Hello everyone. Okay, so this is an example problem where we're going to see both convection and radiation. So I'm going to read the example problem and then I'm going to ask you to pause the video so that you can attempt to solve this yourself, and then we're going to look at the solution together. So the problem statement states that you have a uninsulated steam pipe that passes through a room in which the air and the walls of the room are both at 20 degrees Celsius. The outside diameter of the pipe is 50 millimeters, and its surface temperature and emissivity are 220 degrees Celsius and 0.78 in terms of emissivity. So, what are the surface emissive power and irradiation that is occurring on the steam pipe? And if the coefficient associated with the free convection heat transfer from the surface to the air is 20 watts per meter squared per Kelvin, then calculate the rate of heat loss from the surface of the pipe per unit length of the pipe. And that is because let's assume we don't know what the length of the pipe is. So you can pause this video, think about this, think about how you're going to approach it, and try to solve it yourself, and then we're going to solve it together. Okay, so now let's look at the solution together. First, you want to write down the assumptions that you have. Also, you always want to make a sketch of the problem, but because we already have one, because I've provided it in the problem statement, you don't have to do that. But first, we're assuming that you are at steady state conditions. Also, we're assuming that the radiation exchange between the pipe and the room is between a small surface and a much larger enclosure. And the small surface would be the pipe, and the much larger enclosure would be the room. And the reason why this is helpful for us is because we're going to use the assumptions and simplifications associated with having a small surface and a much larger surrounding, which I showed you when I was explaining the radiation in the previous video. Finally, the surface emissivity and the absorptivity in this case would be equal. So first, let's calculate what is the emissive power, and that is how much radiation energy does this surface of the steam pipe emit to the surrounding. So capital E is the emissive power, and we know that capital E is equal to the emissivity times the Stefan Boltzmann constant times the surface temperature of the pipe to the power of 4, where we have the emissivity could be anything between 0 to 1. And I told you what are the factors that influence the emissivity. You could look at that in the previous video. Now, this problem statement tells us the emissivity of this steam pipe surface is 0.78. Also, we know what the Stefan Boltzmann constant is. It's 5.67 times 10 to the negative 8 watts per meters squared per Kelvin to the power 4. And we know what the absolute surface temperature of the steam pipe is. The temperature in degrees Celsius is 220 degrees Celsius, and in Kelvin, it's 493 Kelvin. And so if you multiply and if you use this emissive power equation, you get a emissive power of 2,612.6 watts per meter squared. And that represents how much radiation energy the steam pipe outer surface emits to the surrounding. Now, we also need to calculate what is the absorbed irradiation power, which is G, and that is essentially the radiation from the surrounding hitting the steam pipe. We know that the absorbed irradiation power is some absorptivity factor multiplied with the total irradiation power, which is G. So the absorbed irradiation is what we really care about, because it represents how much thermal energy is absorbed by the steam pipe. And so the absorbed irradiation power is the absorptivity of the surface, which is anything from 0 to 1, multiplied by the irradiation power, which based on our assumptions, we can assume is that coming from a black body, and so would be the Stefan Boltzmann's constant multiplied by the temperature of the surrounding to the power of 4. And because we're assuming that this is a gray surface, then the emissivity can be equal to the absorptivity. And we know what the emissivity is. It's 0.78. So in this case, the absorptivity is 0.78, and therefore the absorbed irradiation power that the steam pipe absorbs from the radiation of the surrounding is equal to 0.78 multiplied by 5.67 times 10 to the power of negative 8 times 293 Kelvin, which is the temperature of the surrounding walls. Therefore, you have an absolute absorptivity radiation of 325.9 watts per meter squared. Now, if we look at the pipe heat loss, we know that the pipe heat loss is not just due to the radiation heat loss. It's also due to the convection heat loss, because you have air inside the room that is flowing over the steam pipe. So we need to calculate what the convection heat loss is. So if you want to calculate what the convection heat loss is, we look at Newton's law of cooling, which is something I've explained also in the previous video. So you can look at that. Essentially, the heat flow or the convection heat loss flow is equal to the average convection coefficient multiplied by the surface area of the steam pipe, where you have air that is flowing over the pipe, multiplied by the temperature difference of the surface temperature of the steam pipe with the temperature of the air. And so we can expand the surface area, and we know the surface area is equal to pi times the diameter of the pipe times the length of the pipe. And we could rearrange this equation because we don't know what the length of the pipe is. As you see from this picture, the length of the pipe is not given to us, and it's actually asking us to figure out what the rate of heat loss from the surface per unit length of the pipe. So I'm going to move the length over here to this other side of this equation. So we have the heat flow per surface area of the pipe is equal to the average convection coefficient multiplied by 2 pi r, which is the same thing as pi times the diameter, multiplied by the difference between the surface temperature of the steam pipe minus the temperature of the air. And therefore, if you compute that, you will get a heat loss per unit length of the pipe being 1,256.6 watts per meter of pipe that you have inside the room. Now, that is just the convection heat loss. Let's look at the radiation heat loss. The radiation heat loss will be the net radiation. So we've already calculated the emission power, which is the radiation power that the pipe emits, and we've calculated how much radiation power the steam pipe actually absorbs. So the net radiation heat loss would be the emission power minus the radiation absorbed, all times the surface area. So we've calculated 2,612.6 watts per meter squared for the emission power. Now, if you subtract the absorbed power, the absorbed irradiation power of 325.9 watts per meter squared, and you do the same thing with the area. So if you expand that, you have pi dl, and if you move the length to the other side of the equation, because we don't know what the length is, and so this equation will express the amount of heat loss per unit length. Then if you do the math, you get 359.2 watts per meter. Now, if you look at the total pipe heat loss, you need to add the convection heat loss to the radiation heat loss. And so you get the pipe heat loss. The total is 1,256.6 plus 359.2, and that equals to 1,615.8 watts per meter of heat loss of the pipe inside. So if you know what is the total length of pipe inside the room, you can calculate actually how much heat that the pipe is losing inside the room. One of the things that I really like about this example is that it helps you build the right engineering intuition. Because as you could see for this example, you have both modes of heat transfer that contribute to the total pipe heat loss. So you have convection and you have radiation on the other hand. Now, you'd have to exercise your engineering judgment because you might have other applications where you would say the radiation heat loss is negligible compared to the convection heat loss. And in order to say that statement, you need to qualify that by some kind of calculation that proves it. And so what I like about this example is it allows you to see the contribution of the different modes of heat transfer. And so I hope by this example, you're able to appreciate how you can have two modes of heat transfer in one problem statement, and you could analyze the different contribution of each. And I'm excited to go through the other examples I have in this course for you and to teach you the other concepts as well. So without further ado, see you in the next video.